Hello and welcome to another exciting lecture of Math 1. What the hell is it? 140?
140.
Math 140 business or something. And we are now in lecture number.
5.
Is it
5.
are we in the third week already? Wow.
Yeah.
Time flies when you're having a horrible time. Math 140 business lecture number 5. And we're continuing in chapter 3. Chapter 3 began, so chapter 3 continued. It began with the idea of density curves, which are these idealized models, which we hope, are we going in person next week? That's the idea, February 15th. It's a week from today. I'll see you all in person. So that's gonna be really exciting for none of us. Anyway, so density curves are these idealized graphs, these idealized shapes that we believe a population follows. And when we take histograms, hopefully those histograms somewhat resemble these models. In a more sophisticated stats course, you'll be given data and said, hey, what kind of model is this? And you can say, well, let me check if it's normal. Let me check if it's this. Let me check if it's that. And you're trying to fit the data to a specific distribution. Here, you're basically being given a distribution and you don't have to worry about it. So we have this idea of density curves. And then we talked specifically about the normal distribution, which is the most important in all of statistics, also called a Gaussian. Anyone know who came up with the normal distribution?
Gaussian.
Somebody named Gauss.
Someone named Gauss. Anyone know Gauss's first name?
Robert.
Mario.
Mario Gauss. It was not Mario, no. His name was Friedrich Sebastian Gauss, I think. Pretty sure. There's a story about young Mr. Gauss on his first day of school, possibly apocryphal, possibly real. It's been lost to antiquity. But young Mr. Gauss was supposedly about 7 or 8 years old. And he was in school for the first time ever. And rumor has it that the teacher was getting somewhat frustrated with the students that day because they were unruly. So we gave them an assignment. He said he wanted them all to add up every number from 1 to 100. And he was thinking, the teacher, that this would take them all day. They didn't have calculators back then in the early 1800s. They had these little slate boards and they would be able to write 4 numbers, erase, 4 numbers, erase, like it wasn't big, and they didn't have these nice pens where you can be very precise. And before the teacher sat down, apparently Gauss already had the answer, because Gauss realized that if you add 100 and 1 and 101, 1 and 100, that just gives you 101, and 2 and 99, that just gives you 101, and 3 and 98, 101, all the way up to 50 and 51, 101. So this is just 50 copies of 101, which is 5,050. Now, in the grand scheme of mathematics, this is not really that sophisticated, but when you're on your first day of school and you've never learned anything before, education-wise, coming up with that is quite an achievement, I think. And Gauss is considered by many to be the greatest mathematician who ever lived. And yes, Gauss is the one who came up with the normal distribution. We learned that the 68, 95, 99.7 rule, often called the empirical rule. The word empirical means that there's not really a theory behind it. It's just the result that you get from actually doing some kind of an experiment. In this case, if you look at a normal distribution and just do the math, these are just the numbers that you get. There's no deep theory behind it. It's just, this is what comes out of the math. So we did that. And we stopped on page 81. And today we're starting on page 81. with the standard normal distribution. To describe a normal distribution needs three things. What three things do we need to describe a normal distribution? Well, one, we have to be told that it's normal. If we don't know that it's normal, then you can't really describe a normal distribution without knowing that it's normal. So that one is kind of like a freebie. But what are the other two things that we need in order to know which normal distribution we're talking about?
Mean and the standard deviation.
Mean and the standard deviation. So you have the mean and you have the standard deviation. You provide me those three pieces of information and I know immediately which distribution we're talking about. The mean is right there in the center, mu, and sigma is then the distance from the mean to the inflection points on either side where the graph transitions in the center from being sort of like a hill to the sides where it's sort of like a bowl, concave down in the middle and concave up on the sides. Out of all normal distributions, there is one to rule them all. There is one more important than any other. The most important normal of all, normal distribution of all is which one? What do you think out of all possible averages might be the simplest and easiest to work with?
Gaussian.
No, I'm saying which number. I need a specific number for the mean and a specific number for sigma. Out of all
One.
possible averages, which is the simplest you think to work with?
One.
Zero.
One.
Zero. Very symmetric, right along the y-axis, a mean of zero. And out of all possible sigmas, out of all possible deviations, what do you think the easiest is to work with? Numerically,
One.
one.
Zero.
Well,
Zero to one.
it can't be zero because then I won't have any spread.
Right, so wouldn't that be easy?
Well, yes, but it won't be normal either. All right, I still need,
I see.
I still need to have the shape. So the most important normal distribution of all is n of 0, 1. This is called the standard normal distribution. And it is denoted by Z. So when we talk about a normal distribution, I might say, for example, oh, suppose X is normal with mean 17 and sigma 3. Or I might say, suppose we have Z. And Z just is immediately known to be a normal of mean 0. Mean 0 and sigma 1. I don't got to say that. It's just automatically. The distribution Z, when I see that, it's normal, mean 0, sigma 1. Why is it so important? Well, before calculators and computers were so prevalent in society, calculating probabilities, like what's the likelihood of being less than this number or greater than this number or between these two numbers, was a lot harder than it is now. And people had tables of normal distributions. And you look it up on a table, something like, did I show you this last time, a Z table? Did we ever use it before? Did I talk about it at all?
Not in this.
No,
course.
you haven't mentioned it.
Okay, so this is a typical Z table. And what it is if you look on top, you see a basic Gaussian shape, a basic normal distribution shape. Look in the very center. What is the mean according to this shape?
0.
0. Okay, and they call it Z. So without even telling me that sigma is 1, I know sigma is 1. And if I want the probability that I end up with a data point less than or equal to a specific number Z, what I would do is I would find Z in my chart. So for example, let's say I asked for the probability that a data point was less than or equal to negative 1.63. How would I calculate with the table the probability that a data point taken from this density curve, this distribution, would be less than or equal to negative 1.63? My goal,
0.0516.
I'm sorry?
Is it 0.0516?
Yes, and can you tell me how you got that?
Go to 1.6, and then the second, the hundredth would be 0.03.
Good. So if you look,
1.63.
excellent. So if you look in the left column, it tells you Z. Also on the top, it tells you Z. So I'm going to put them together. I'm going to put negative 1.6. I'm going to find that in the left column, negative 1.6. And then the second decimal, the 3, I'm going to find in the top row, 0.03. So then if I want negative 1.63, I just see where those two meet. And it's at 0.0516. So there's a 5.16% chance, at least approximately, that a data point taken from a standard normal distribution would end up being less than or equal to negative 1.63. And if I want more than negative 1.63, how would I do that? Because this table seems to only give me to the left of a point. It's like a leaf plot a little bit, but I mean, contextually different. It's just a way to use this chart to calculate a
Can't you
probability.
just subtract the number by 100 or 1?
Yeah, exactly.
Just
So
to
if
get
I
the
want,
opposite.
Yeah, 1 minus.
it's 1 minus that. If I want to the right of a point, it's 1 minus what it is to the left. So sometimes, you know, little common sense and an understanding of what's going on, you can calculate other probabilities besides just the one in the table. Now, how many tables would I need to consider every possible normal distribution in existence? Remember, the mean could be anything, and sigma could be anything positive. So how many different possible normal distributions are there in theory to represent every possible normal curve in existence?
Isn't it an infinite amount?
There's an infinite number of them, right? Because there's an infinite number of possible means, and every one of them will have a infinite number of sigma, so it's doubly infinite. But I can get away with only using the standard normal and not needing all of the others, because I can convert any normal. It is possible to convert any normal into Z.
And Professor, what does that mean?
The capital N.
No, sorry. Like, what does it mean to that any normal can be a Z?
That means when it comes to actually calculating probabilities, I don't need a table for every possible normal. I can convert any normal into the standard normal and then just use that to get my answer without needing one for N, for mu is 17 and sigma 3.6. And another for mu is 26.2 and sigma 2.9. And another one for mu is negative 1.7 sigma. I don't need to worry about that. I can convert any normal into the standard normal and calculate the probabilities that way. Now, nowadays with the TI-84, this technique is not as important because I can just plug in whatever mu and sigma I want in here, and it's going to do the math for me. But historically, I didn't have that. So how do I convert a normal to anything else? And the answer is I compute what's called the Z-score. The Z-score, which is lowercase z, is given by a very simple formula, x minus mu over sigma. Your data point, x is your actual data value. Mu is the mean according to your normal, and sigma is the standard deviation according to your normal. So what I can compute is the z-score for any data that you possibly have. And we're gonna see in a minute that I can use Z to calculate probabilities. But before we do that, let's just do some examples where we actually see the usefulness, even in this day and age, of this particular process.
So it's
So
kind of like a shortcut.
it's certainly a shortcut, but it's not just a shortcut because it has its usefulnesses. So I want to do an example to demonstrate that. So let's do the following problem. Heights of women 20 to 29 in the US follow a normal of a mean of 64.2 inches and a sigma of 2.8 inches. Two women, one 70 inches and the other 60 inches, walk into a room. Which one is more unusual in the sense of being further from the mean? Now, if all I want to do is calculate how far they are from the mean, it's kind of easy. How far is the 70-inch one from the mean? How far is she from the mean?
Well, that's 3 deviations.
5.8 inches, right? 70 minus 64.2, she's 5.8 inches away. And how far is a 60-inch one from the 60-inch one away from the mean?
67.2.
4.2.
4.2, 64.2 minus 60, correct?
Oh, shit, yeah.
Right?
Yeah.
So one is 5.8 inches from the mean and the other is 4.2 inches from the mean. So obviously the 70-inch one is more unusual. But as a follow-up question, are either of them far enough from the mean to be an unusual result in the sense of there being less than a 5%, a 2.5% chance of being that tall or short or further from the mean. So we know that one's 5.8 inches, one's 4.2 inches, but are either of them so far away from the mean that we consider it an unusual height? And what does an unusual height mean? That means if we look at the normal curve and we say that the mean is 64.2, is one of them so far away on either end that the chance of being past it would be less than 2.5%. Not really an outlier. Well, yeah, actually, yeah. Okay, that's a good way of thinking about it. An outlier, someone who's just so far from the average that it's like, this is just unusual. So the way we determine this, or the way that we're going to determine this, is by calculating each of their z-scores. So let's calculate the z-score for the 70-inch woman. We'll call it z70. We take her data point, which is 70. we subtract the mean, and we divide by the standard deviation. What do I get when I do that?
2.07.
2.07. And if I take the 60-inch woman, and I calculate her z-score, which is 60 minus 64.2 over 2.8, what does that give?
Negative 1.5.
Negative 1.5. So what's the cutoff on either side of a Z distribution? What's the cutoff on either side of a Z distribution to be in the outside 2.5%? At least approximately.
3
This is
standard
last time.
deviations.
How much?
3 standard deviations.
Not 3, 2. Because remember, the first deviation is 68%. The second deviation is 95%, correct?
Okay, I get what you're saying.
Right? So if I hit 95%, leaving 2.5% on either end, then 2 and negative 2 are the cutoffs for being considered to be in the outside 2.5% on either
Oh,
end.
I was assuming everything after the 99.7 would be the cutoff.
No, 99.7 is the terminology for almost all. But when we talk about something that's unusual, we usually are referring to the inside 95% is a usual result. And that's why when I said here, I said unusual in the sense of there being a 2.5% of chance of being past it. We usually consider the 2 deviation cutoff to
Okay,
be
okay.
unusual.
Alright.
So
Thanks for the
given their
clarification.
given their Z-scores, are either of these 2 women unusual in that sense?
Yeah, the
No.
first one.
Yeah, the 70-inch woman with a Z-score of 2.07 is falling in that region of unusualness.
So she's an outliner.
Well, you can call her an outlier. I mean, outlier just means something outside the norm. So yes, you can call her an outlier. She might not appreciate that, but you know, I'm not sure how your game is. Mine's pretty bad, so I'm not gonna do that. So 2.07 falls in that region where we call it an unusual result, whereas negative 1.5 falls in that region, which is not an unusual result. So by calculating the Z-score, it's a lot easier to determine whether or not the result is unusual. If it's past 2 or negative 2, it's an unusual result. If it's not past 2 or negative 2, it's not an unusual result. So what does the Z-score tell us? It doesn't care what the actual data point is. What the Z-score gives you is how many standard deviations away you are from the mean. A Z-score of 2.7 means 2.07 standard deviations above the mean. And negative 1.5 means 1.5 standard deviations where?
Below them.
Below the mean. What would the Z-score be for the mean itself?
0.
0. So what the Z-score does is it takes your original distribution with unknown cutoffs, and it allows us to convert it to a standard normal distribution where I know exactly what the cutoffs are. They're negative 2 and 2. And even better than that, I know exactly how far you are away from the mean in terms of standard deviations. Are you within 3 deviations from the mean? In which case you're just about everyone, or are you even past that, Philip?
So in what sense would this be used? Like trying to find out what the outliers are?
No, I mean, I've heard this outlier a few times today. We're not really calling them outliers, but yes, if you're past 2 deviations, it is considered an outlier. We're going to see that this is used throughout the course because here's the idea, which this is weeks away, but here's the idea. Suppose I'm curious. whether or not the majority of Americans want stricter gun control laws here in America. And somebody comes along and says, you know, I don't think, I think it goes 50-50. I think some people do, some people don't, but there's no leaning one way or the other. So they say, I think it's 50-50, 50% want it, 50% don't. And you're like, no, 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 no. I talked to a lot of my friends and I've seen a lot of news coverages of this and that. And I really think that more than 50% want stricter gun control laws. So I'm going to take a survey, a sample, and I somehow make it what I believe is representative of America. And I get this result. I'm going to try to take my results and infer from my result whether or not I believe what my friend is saying or what I'm saying. How am I going to do that? I'm going to compute a z-score for my sample. And if my z-score is past 2 or -2, then that gives me a result which I think is unlikely to conform with the belief that my center is really some value. And I think it's going to be less or possibly more. So we're going to be using z-scores later in the course to basically answer all of our questions about whether or not we think that something is true or not. I know that was a little vague because I'm not really teaching it right now, but hopefully it gives you at least an impression of what we're going to need this for. Philip, question? Not Philip, I'm sorry, I meant Peter. Apologize.
So what in the problem says that it's the cutoff is 2?
That's
You
just what we say. As statisticians, we say anything past 2 is unusual. Nothing in the problem set, but that's just the way that's what we say. We say
would
2.
would you be able to do another example like this?
Finding Z, trust me, we're gonna be doing this the entire semester. Z-scores are gonna be a huge thing the entire semester. I promise you, we're gonna have lots of them. Maybe even more today, we'll see, but we're gonna have plenty of them. You're gonna see them in action. For now, all you need is this formula right here. That's all you gotta do. If you have the mean and deviation of your distribution and you have your data points, you can calculate your z-score. What does your z-score tell you? How many deviations you are away from the mean. If it's past 2 or -2, it's an unusual result. If it's not, it's usual. That's all we have to worry about so far.
So unusual would mean a less than 2.5% chance of X being,
No, unusual means the chances of that result occurring is less than, or anything even more further than that point is under 5%. 2.5% on this side, 2.5% on that side.
Okay, so I understand that greater than 2, less than 2, but why is the 2.5 important?
Well, that's just a choice. That's just a choice that was made.
Okay.
I mean, long before you or I came along, we decided that 95%, that's going to be the cutoff for what's usual. And that corresponds to a -2.
Oh, so the 2.5 comes, okay, I understand where that 2.5.
Yeah, the 2.5% comes from the 2 and the 2 and the 2 comes from 2.5%. They go back and forth. Mark, go ahead.
And Professor, in any equation that involves z-score, that 2.5% cutoff and the past -2 or sorry, less than -2 or more than less than negative or more, sorry, more or less than 2, is it in every single z-score formula?
No, that's just I mean, the z-score formula is just calculating a z-score. That's it. It's just a formula. How do I get the z-score? Oh, the z-score is this. If I want to interpret that z-score and say, is that z-score, does that correspond to an unusual or a usual outcome? Then if it's past 2 or -2, it's unusual. If it's not past 2 or -2, it's usual. Why is 2 been chosen? Because someone a lot smarter than you and I decided that we want 95% to be considered usual and the outside 5% to be unusual. And how do I get the outside 5%? By cutting it off at 2. That was a choice that someone made.
So anything -2 or 2 is unusual, and anything that isn't that is usual.
Well, if it's not bigger than if it's not smaller than -2 or bigger than 2, it's a perfectly reasonable result. If it is, it's an unusual result.
Thank you.
Okay. I mean, what percent of your population is going to be between -2 and 2? This is from last time.
95.
95.
95%. So 95% of individuals are between -2 and 2. So whoever it was who decided that the unusual nature of a result should be the outside 5%, you can blame that person for picking the cutoffs to be -2 and 2.
Can the cutoffs be 0.35%? Or how much it was for three deviations?
To be what?
Because we know that three deviations is 99.7%, yeah?
No, you can't change the way statisticians do it.
Yeah.
Right? We don't have the control of that one. Now listen, if you think that unusual should be that, knock yourself out, have a good time. But in any stats book that you come across or a test where they say, hey, is this result unusual? And you say, well, I personally consider 4 deviations to be normal. Well, you'll get it wrong because this book and every stats book says it's just 2. Anything past 2 is unusual. Anything within 2 is a normal and a typical result. And when we get later in the course to confidence intervals and hypothesis testing, which I mentioned on the first day, we're going to see that that 5% value is going to be used almost all of the time. And therefore, we're just going to go with it from right now. The outside 5%, unusual. The inside 95%, that's a normal result.
So the
Okay.
z-score has to be greater than -2 and less than 2
No, to be normal or to be not normal?
to be a usual.
To be a normal or usual result, I don't use normal as normal curve. I just mean normal or usual results has to land somewhere in this region here. That's between -2 and 2. This woman here, -1.5. Perfectly fine.
Right, that's what I said. So
Yeah.
greater than -2 and less than 2.
Yeah. I mean,
But isn't that 4 z-scores away?
for
There's a
Z,
spread of 4.
2 to the left, 2 to the right.
Right, there's a spread of 4.
Yeah, a spread of 4 deviations
Okay, so
That's
2
right.
standard deviations in both directions.
in both directions. That corresponds to 95% of your data in any normal distribution.
Got you.
Okay. Let's do another one. I sense some confusion here, although I think you're making it a lot more complicated than it actually is, but who am I to say? So let's do another example here. Scores for high school seniors on the SAT. So scores, we'll call it S, follows a normal distribution with a mean of 1010 and a standard deviation of 214. What percent of seniors score at least 820? And I want to do this in a few different ways, just to show you our options here. What percent of seniors score at least 820?
Professor,
Yeah,
so just to understand your notation, so N is normal distribution of with a mean of 1,000, standard deviation of 200. What does S stand for?
oh, that's what I'm calling this example, this distribution. I'm calling it S for scores.
Oh, okay. There's so no significance.
That's my label. My label is S for scores. If you want to call it S for SAT, if you want to call it L for
Lasagna.
lasagna, then call it out. It makes no difference. It doesn't play any role. Now, where does 820 fall on this distribution? Where is 820 on this density curve?
On the left.
Okay, can we be a little more specific?
To the left of the mean.
Well, that's
Within-
what I assume that's what you meant by
Then
the
one
left.
deviation to the left.
One full deviation, because one full deviation does not take me to 820.
No, it's two.
Well, one second. If I go one deviation out, if this is sigma, then what number is that right there? I saw someone say negative 0.89. We'll get to that in a second. I haven't done any z-scores yet. I'm just asking what is one sigma to the left? What is that data value of
What
one?
was that? 896?
I got 796.
796.
Yeah,
10,
796.
20 minus 214, 796. Right? Right? You agree?
Yes.
So 820 is about here somewhere. So that's about, this is about 820. And I want to know the percent that score above at least 820. So I'm looking for the percent of seniors, assuming this model is correct, I'm looking for the percent of seniors that score greater than 120, at least 820. I'm looking for the percent that score in there. Now, even if we don't do any math, could someone give me a lower bound for my answer? It's definitely at least this number.
At least 60%.
At least 50%, because if I stop here and I just do the right half of the curve, it's already 50%. Oh, no. Oh. I hit it one more time. No.
There's no
Anyway,
redo.
I've been
Profe-
looking for, I can't find a redo anywhere. Which one-
Professor, I got 68.6%.
How do you get that?
So I counted how many percent is two deviation. So two deviation is 428. It's 47.5%. We divide in the two deviation by 47.5%. So we're getting that one point is 9%, like something like that.
Well, it doesn't really work that way. If you're trying to use the 68, 95, 99.7 rule, you can
No,
only,
no, not like that.
I mean, it's hard to do it by eye. I mean, if you're right, I'd be very surprised. I don't think it's correct. Let me do it my way and we'll see if we agree. And if we do, I'll go back and I'll look at it more in depth because what I heard doesn't sound right, but maybe it is. We'll do it in two ways. The first way, we're gonna go directly to our calculator. So where do I go on my calculator? Anyone remember?
The data, right? You hit the data.
Not data. No, I don't need any data here.
Graph.
Don't need any graph.
Stats.
Stats. Well, I don't know. Sorry, not stat. It's not stats. Sorry. We did this last time. Anyone recall the second? Yeah, there we go. Second. Vars. And then where do we go from there?
Normal CDF.
Normal CDF. And then what do we put in?
The lower would
What's my-
be
What's my lower?
820.
820.
And then the upper would be those 7 9s or whatever that you had last time.
The upper, just a bunch of nines. Okay,
The mean is the 10 10, and then the standard deviation is the 214.
214. And what's my results for the probability or the percentage that falls in that pink region?
0.813.
Yeah, so 81.3% approximately.
And then when you
Armin,
answer, you would say
Hold on, Armin, was that what you said? 80, I don't get 80.19, I get 81.3.
yeah. On the z-score graph thingy, it's 81.33, so it doesn't matter, right?
On the what score?
The z graph, I looked up the
Oh,
PDF table.
you mean the table?
Yeah, to the
Well,
table, yes.
We'll do that in a second. We'll do that in a second. This is just the calculator approach. So second var is normal CDF, 820 to a bunch of nines, 10, 10 mean, 214 deviation. I got 0.8126. I'll write out exactly, or not exactly, but at least all the decimals. I get 0.8126 0.894424, which is about 81.3%. Now, the other way we're going to do it is we're going to convert to a z-score. If I look at a z-score or a z distribution, what's my center now going to be?
1010.
I can't hear you.
1010.
No, 1010 was the original data. This is S.
Zero.
Now Z, this is
Zero.
0.
0. Yeah.
When I convert to a standard normal, my mean becomes 0. What does my 796 become?
One.
Negative 1.
Negative 1. Yeah.
-1. And more specifically, what does my 820 become? This is the one that Philip said earlier. What does my 820 become?
Negative 89. 0.89.
0.89. And what I'm looking for is, again, I want to know the probability of being past negative 0.89. Now, were there any decimals with negative 0.89 or was that exact?
The decimals were 0.1867.
Okay, so let's get to 3. So 0.8878 and so on. Just to have a slightly more precision.
How did we get 0.8878?
We converted to the z-score. We did, so this is option number 2. We did z equals data minus mean divided by standard deviation. And this gives me negative 0.88785 and so on.
So Professor, the second way would be the easiest, correct?
Well, I don't think anything beats the calculator. I mean, the calculator approach, we had our answer in seconds. Right? I mean, assuming you know how to plug it into the calculator, it was very quick, right? This one is a little bit of work. Not too much work, but a little bit of work.
Because the second one, I see what you're saying. The second one, you have to plug it into the formula and then the calculator, correct?
Well, we're not going to use the calculator because if I was going to use the calculator, I would convert to the z-score. What's the point? The
The
second way,
second for the Z table.
yeah, it's a z-table. So let's remember this number, negative 0.88785. So now I'm going to go here to negative 0.88785. And it'll be approximately, at least, negative 0.88 is 0.1894. And negative 0.89 is 0.1867. I'm somewhere in between them, but which one am I closer to?
The 9.
The 9 by a significant margin, right? So I'm gonna guess.
How did you find on this table? I'm lost.
So on the left column, you see it's Z and you see negative 0.8.
Yes.
And now on the very top, you see the second decimal 0.08 or 0.09.
Oh, okay, I see.
That corresponds to negative 0.88 and negative 0.89. So it's somewhere between 0.1894 and 0.1867. I'm going to guess about 0.187. It's significantly closer to the second number than the first. So about 0.187, which means being on the left is 0.187. So being on the right is how much?
81.33.
0.813, which as you can see is exactly, or at least approximately what the calculator gave me. So if I'm going to use the table, I got to convert to Z. And then once I have Z, I can use my table. If I'm going to use the calculator, I don't need to worry about it. I don't need to convert to the Z-score. I just go directly to the table. So much easier.
How did you know that the left is 0.187 and then the right is 0.813 without
Well, they
doing
have to
those?
add to 1. I mean, the total area under the curve is 1. That's one of my 2 conditions for a density curve. So if to the left is 0.187, to the right has to be 0.813,
Just
Oh,
take 1 minus.
right? 1 minus that. And my Z table here gives me to the left, as you can see in the picture. Some tables online give you to the right. You got to see which one you're dealing with. Yeah, Philip, what's up?
So just making sure you first use the formula, which is the data, and then the I forgot what it was, but use the formula, yeah, the data, then the mean over the
Oh,
sigma, right?
Give me 1 second, please. Give me 1 second. Hold on. Okay, sorry about that, everyone. Might be a gas
No
leak.
gas leak?
I can't smell it. So if suddenly, you know, everything goes blank and static, it was nice knowing all of you.
I mean, you can't smell oxide, so
I mean, it smells, doesn't smell like clean, fresh air, but I can't, is it a cleaning product? Is it a gas leak? Is it something? I don't know. So I'm just gonna hope, and I'll leave here very shortly and hope nothing explodes before I leave. But meanwhile, Philip, do you have a question as, right before that interruption, or anything you're not sure about, or anything anyone's not sure about?
Yeah, I
I
have a
was-
question.
I have a,
Go ahead.
Yeah, go first. That's fine.
no, you're good, brother. You're good. You're good.
Okay. So why did you do one standard deviation? I thought to get to the 95, you have to do 2 standard deviations.
I mean, why did I put -1 in? Just to kind of give a reference for where 820 is located. There's no other reason.
But okay.
I could have left out 796 and -1 and done exactly the same thing. I just put it in there just to kind of give you like an idea where 820 lands, so that when we get our answer at the end of the problem, we can kind of say, oh, okay, that seems reasonable.
Yeah, so if you're looking for unusual, then you would put 2.
If I'm looking for unusual, I would just look at my z-score. I wouldn't even make a graph. I would just check my z-score. And if I got something past -2, I'd say, okay, this is unusual. But even if it was unusual, that doesn't change the fact that we're just asking what percent of seniors score at least 820. If it
Right,
turns
but what
out
if you're
that
saying what percent of seniors are fall outside the usual range?
that would be a whole nother question. In fact, you know what? That's a great question. Right when this is over, let's do that one. Just for fun, because this is all fun, but we'll do a little more fun. We'll answer the question, what percent of seniors score outside the usual range? I love it. We'll do it in a minute. Philip, question?
Yeah, so when we have a test, are we gonna have the Z table with us?
No, you'll have your calculator.
Okay,
Z-table is completely unnecessary with the advent of calculators.
Okay,
There's
but like, will we have
no-
questions where we're not allowed to use a calculator?
There's no
So we have to use the
questions. There's
table.
no questions where you're not going to be allowed the calculator.
Okay, so it's pretty much useless.
Oh, I mean, I know other teachers
The
that,
battery goes dead, you'll appreciate it.
there you go. Or if you're ever stranded on a desert island and you don't have your calculator, but you do have a book on statistics, again, you'll be very appreciative. So there are unusual scenarios. I'm not sure what their z-scores are, but there are certain situations where it might prove useful to understand how tables work. But in general, the calculator does all the work for you.
I have one more clarification question. So there's, to be usual, it should be within 2 z-score, like, but let's say you're just not converting to a normal or to a standard
Normal?
distribution.
Yeah.
So it would have to fall within 2 standard deviations. So like on this one, 214 would be within 428 and then within -428 or something.
No, I think it would be
Or-
580, no?
Well, it would be 10. It'd be 1010 plus 428 and then 1010 minus 428.
Something like that, yeah. Yeah, that's exactly it. But again, you guys are.
Okay, so anything above or below that would be unusual.
Right,
Or outside of 2 standard deviations.
right. But again, you guys seem to really focus on this unusual versus usual thing. It's just an arbitrary cutoff. And unless the question specifically says, is this unusual or not, it doesn't matter. Your mathematics will be the same no matter what.
But I'm just saying within 2 deviations. That was my point.
Yeah, that's just, those are, and we'll do that in a minute as soon as all the questions are answered. Yeah, Mark, go ahead.
I'm so sorry. I'm still lost on the first part where you plug in second vars normal CDF.
Yeah.
What do you plug in after that? My calculator, I just see normal CDF and then
Okay,
it has a.
so you don't have the same version that I do.
The one 83, right?
Yeah, well, I have an 84. With an 84, it gives you a list where
Oh,
you can
shit. yeah,
plug
I
in
didn't do that.
lower, upper, and so on. The one that you have, I believe, takes you directly to something that looks like this, but without numbers filled in.
Exactly that. Yeah.
Yeah, so you gotta fill in lower, upper, mean, and sigma with commas in between. You gotta do that manually. You gotta put in normal CDF and then put in 820, comma, a bunch of nines, comma, 1010, comma, 214, and then hit enter, and it will give you the same value. It's just not as user friendly as the TI-84.
That sucks. Okay.
Now, for you, not so much for me, it's a you problem, but that's okay.
Wait, what calculator?
TI-84 plus C, or his calculator, or someone's
Oh,
free.
no, I had that one. What?
Yeah, I had the T183, but I bought this like 5 years ago.
Oh,
If you're doing it in Excel, what's the function?
I'm pretty sure if you're on Excel, you would do equals. And then if you start typing normal, it'll probably give you a list of options, and it should be pretty self-explanatory which one it is. It might even be normal CDF.
Okay.
And then as usual with Excel, it will tell you what inputs it needs and what each
Right.
input is referring to.
Okay, so it'd probably be like lower, upper, sigma.
Could very well be. I don't know the order, but it should be something similar to that. Vin, go
Right.
Can
ahead.
you say,
Okay.
So at this point, honestly, I think I'd rather just blow like a TI-84 calculator because I think
I
I'm
would-
that lazy to do the.
I would buy it,
option.
use it, and then sell it, because whatever you spend on it, you'll make back at the end.
Yeah, for sure.
Or just rent one. I think you can rent one from school, from the library or the bookstore for whatever. If you buy it and sell it, you'll make back what you spent. If you rent it, all that money's gone. I would personally buy it. Hey,
It's $130.
you want to keep it, huh?
It's $130.
164?
Wait, it's
That's
164?
so insane considering it's 20 years
it's
old.
130, it's 130 in Target.
I don't even remember paying
30,
that much.
right?
That's crazy.
130 plus tax.
No, without.
Seems a little
Also
excessive.
130 without tax. So you
And
gotta add
Allison, I'm
another
sorry
50.
that you're broke. That's horrible, but just be aware, I wasn't even joking. I was completely serious about that one. But just remember, it has extremely high resale value. So if you bought a used one for whatever you spent, you can sell it for the same amount. If you buy a new one, you might not be able to make exactly the same amount, but a ballpark. Anywho, back to this question. So I forget who it was. I think it was I don't even know, but follow-up question. What scores
Considered unusual.
would be considered unusual? So here, we have to work backwards. We have to start with the Z-score and then figure out what the data point would be. So I know that, for example, a Z of 2 is one cutoff for unusual, correct? So the question is, what data point in the original distribution would correspond to a Z-score of 2? So what I need to do is go back to my Z-score formula. What was my Z-score formula again?
N
X
minus
minus, shit.
Data minus
mean over the standard
deviation.
And solve this for my data points.
Why did you put a 2
Yeah,
equals?
I was just about to say, is that a 2 or a Z?
That's a 2.
Yeah.
Why did you put
Because you want it to be, the Z has to be 2 or less, or 2 or
Yes.
more, right?
Because the cutoff points for unusual are 2 and -2, right?
right?
So if I'm doing 2 first, I'll do -2 in a second. I'm gonna
Wait,
do both.
can you do like 2 times 214 plus 1010?
That's exactly what you
The
do.
same one, yeah.
Exactly what you do. So what is the data point that corresponds to a Z value of 2?
1438.
1,438. And what's the Z score that corresponds to a Z score of -2?
How did you get 1438?
I multiplied 2 times 214, then added 110, 1010.
It
Right.
will be 582.
And it'll be 582. cross multiply and then add. You're solving for X. You're solving for your data point based upon your understanding or your knowledge of what the z-score is. So because I have a z-score cutoff of 2, that's my unusual cutoff. I can work back from knowing the z-score to the data point using the same formula, but I got to do a little algebra. And I get that an unusually high score cutoff is 1438. And I can do the same thing with a z-score of -2, which is on the other end, and get an unusually low score cutoff of 582.
So anything above 1438 is unusual. Anything below 582 is unusual.
That's correct. Only 2.5% of seniors are going to score more than 1438, and only 2.5% of seniors are going to score less than 582. Philip, question?
Wouldn't it be negative 582?
How can you get a negative score?
Well, I don't know. I mean, because it's x minus 1010.
Yeah, but you do -2 times 214, which is -4 something, and then you add 1010, it becomes a positive number.
Oh, because I just saw the 2 on top. I thought the bottom was 2. I didn't see it was -2.
I understand.
So professor, for that top one, that +2,
Yeah,
it would just be 214 times 2 plus 110.
1010.
Oh my gosh, yes, sorry. Yes, 1010.
It's okay. Numbers are hard. I get it.
Might be going a little backwards, but why are you adding 1010 if it's negative?
X minus 1010. How do you get X by itself?
Oh, yeah.
The inverse.
Yeah, you got to do the inverse operation, right? So if you want to remove the minus 1010 from the X, you got to add 1010 to both sides.
Okay.
Agreed?
Isn't that more work than just adding and subtracting 428 both sides?
Well, if you know that you're looking for a z-score of 2, then yes, you can do it that way as well. This is a little more general when it could be any z-score. If I said, for example, hey, I'm just curious, I got a z-score of 1.3. Is that good? Well, let me compute your score. And it's a little harder to just add a certain number, but this way would do it. Does that make sense?
You kind of lost me with the 1.3. With the 1.3, if I were to calculate the z-score, I would just go on the you can like use the z-score chart. You can
No,
figure out
no,
the
no, no,
percentage.
no, 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 no. You can't use a z-score chart. I'm not
All right,
looking.
so would you say that it's within 2 standard deviations of the mean?
Yeah, I don't care if it's unusual or not. If I walk in and I say, hey, guys, I just got my score back. I got a 1.3 z-score. And I go, great. What was your actual score? How would you compute that?
I understand what you're saying now. Okay.
Right? The only way to do it is via the formula. You take 1.3, you multiply it by 214, you add 1010, and you say, hey, that's a 1288. Isn't that amazing? I got a 1288. Actually, that is pretty amazing. It's not horrible. It's higher than mine.
Where did 1.3 come from?
Just an example. I was just trying to pick a number that's not just a simple add this many deviations to it.
Professor, I have a question.
Yeah.
So in this case, when solving for both the positive and -2, we got the 1438 and the 582. So what would we do?
You would do anything.
Aren't
You're
those-
done. You would do anything. Just you're done. Those are the cutoffs. Anything
Oh,
1438, anything past 582, unusual, done. It's over.
Okay, so both scores are unusual because they're past two.
Those are the cutoffs. Anything past those scores are unusual.
Oh, yes, yes. Cool. Okay.
Right? Those are the cutoffs. Anything past this or past that, those are now unusual scores. Let's do one a little more complicated. Because, this is fun and everything. And, I know that all of you are just saying, hey, let's ramp it up a little bit.
Is this the continuation or a new problem?
This is a new problem.
Isn't the first one 1428?
Well, 2 times 214 plus 1010 is 1438. Unless my calculator's been wrong every time.
I got the same thing.
Isn't it 2 times 214 plus 1010 if you're just doing it
Yeah,
that way?
yeah.
214 times 2 is 228, isn't it?
Is
428,
428 wrong?
yeah.
Oh, plus the 10 from the 1010. I'm an idiot. Okay.
No arguments. Okay. So, here we go. High levels of cholesterol in the blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol, so we're going to call it capital B, is approximately normal, with mean 170 milligrams per deciliter. I don't care about the units. I mean, the problem cares about the units, but I don't care about the units, with a standard deviation of 30. So, ready for this one? Calculate the IQR. Boom, mic drop. Calculate the IQR.
What is the IQR?
Back to the Q3, Q1
Yes,
situation.
IQR, the interquartile range is Q3 minus Q1. That's going to help us. So now in order to calculate the IQR, I got to calculate Q1 and Q3. How do I calculate Q1 and Q3?
Is it Q1 2
Sorry.
So you have to find the medium. Find the medium of what's to the left of Q2, right? That's Q1.
Okay, that's a great idea. So far,
And
so
then
good.
to find Q3 would be solve for the right or find whatever's on the right of Q2.
Those are all correct statements that you're making. I'm not arguing with anything you're saying. I wouldn't use that to do it because it's a little hard. There's an easier way, but it's not wrong what you're saying. It's just not how we're going to solve it.
Okay, I'm gonna wait then. I'm gonna wait.
No, listen. Being wrong or being right should not be the determining factor of whether you try to attempt to answer a question. Okay, you don't learn as much by sitting silent and waiting for someone else to give the answer. The people
That'd
who
just be one
best-
standard deviation on each side.
hold on. The people who do best in my class or any class in math are the ones who participate verbally. Okay, so if I shoot you down because it's wrong, doesn't mean that I'm unhappy that you tried. It just means I hate you and you're wrong. Philip, question?
Yeah, so 170 is the mean, right? So that's the middle number. So that's
170,
Q2.
yeah, so we can always start. So let's see what we have here, right? I mean, what Mark said was correct. I'm not going to include it because I don't need it, but yeah, the median is 170 because we know that for a normal distribution, the mean and median are both at the center. That's true. This is Q2, the median. Okay.
So would you just add 30 and subtract 30?
Yeah.
30,
Find
if I go 30 to the
Find the
left, 30 to the right, 30 to the left is not 30 to the left and 30 to the right gives me what percent? 68%, correct?
Yeah.
But isn't the IQR the middle 50%? Right? If you make a box plot, isn't this 25%, 25%, 25%, 25%? So the IQR should represent the middle 50%. But what you're giving me right now is the middle 68%. I don't want the middle 68%. I want the middle 50%. So I want something more like this, the middle 50%. So how can I use my knowledge of what I've learned so far to determine the middle 50%? So question, if this is the middle 50%, what is this part here?
25.
25%, correct?
Yeah.
That was a clue. Anyone?
Also, would you put the would you solve for the with 25%? Can I translate that to a score?
Okay, how do I figure out the point that corresponds to 25% being to the left of it?
Solve for the right and then subtract.
It's not gonna help me. Okay, let me rephrase the question then. How do I find the point where 75% is to the right?
I'm sorry, I have a question.
Yeah,
Can you say the IQR is it 44.1?
oh, I don't know. I haven't done it yet. Let's see. Give me a second. So I'll use my calculator to cheat, and I will show you in a minute how to use your calculator to do this. So hold on, we want the 50%. What's the mean again? 170, what's sigma 30? So your IQ hour is how much?
44.1.
No, I don't get that.
Could you just do like 1.5 standard deviations each direction?
1.5, that's a good guess. Is 1.5 deviation 50%? I'm not sure. Maybe it is, maybe it's not. Chances are it's not. I mean, it's a good guess. We know one deviate, well, wait a second, hold on. We know one
Well,
deviation.
3 or 99.7, then half of that is close to 50, right?
Doesn't work that way because it tapers off. It tapers off considerably,
Oh,
not uniform. So here's how we're gonna do it. Ready? Let's find the z-score that corresponds to a proportion of being 25% of being to the left. Do you see anywhere in this table a z-score?
Negative 0.67.
Try again,
Negative 0.67.
try again. Or maybe I made a mistake. Sorry, hold on. I was looking at the wrong thing. What do you say it was?
Negative 0.67.
My
25.14.
apologies. Yes. Sorry, I was looking at the wrong thing. I was looking at
All
two.
right. Everyone makes mistakes.
I did once before. It was a horrible day. 1982. I remember it so well. It was raining. Anyway, so we want 25% to be to the left, correct?
Yeah.
So we look in the table for 25%. And yes, you can see it close to the bottom. There's no exact 25%, but it gets fairly close. You can see 0.2483 and 0.2514. You see those two numbers?
How did you find that on the Z table again?
Look at the fourth row from the bottom, the second to last column, third to last column. You have 24.83%, 25.14%. It seems to be like right in between them, should be roughly 25%, correct?
Wait, how you find the negative 0.675?
Like, how do you know how to look?
I'm telling you, first, look in the table
Yeah.
and find 0.25.
There isn't. There's like 2.5 and then
yeah, you're gonna estimate in between those two.
Yeah. So first find the two numbers that are on either side of 0.25.
0.514 and 0.2483.
Yes, they're in the fourth row from the bottom, the second to last and the third to last column. Do you see them?
It'll be negative 0.6775 or something.
Okay, so we will take as my z-score for this point, negative 0.675. And by symmetry, without actually doing any math, what is the z-score for that point?
0.675.
Positive 0.675, because if one side is 0.675 standard deviations below the mean, the other one is 0.675 standard deviations above the mean. Now,
How did you get negative 0.675 though?
from the table.
No, yeah, I know you got it from the table, but I'm saying, why did you go to negative 0.67? Why did you land on that number?
I'm just looking at this entire, I see like 100 numbers here, right? 300 numbers here, whatever it is. Find 0.25. Just look at everything and find 0.25.
Oh, we're just finding point. Okay.
Finding 25%. Just find it.
Finding 25%.
Right? So the numbers get bigger as we go down. So we're just looking, oh, there it is. Well, not exactly, but those two numbers are fairly close, about halfway in between them. So what are their z-scores? Negative 0.67, negative 0.68, and let's do negative 0.675. Now, what is the value of x that corresponds to negative 0.675? How would I solve for that?
Plug it into the other formula.
0.675 equals
X minus
uh,
170.
170.
over
Divided by
What's
30,
the
yeah.
data point?
Yeah.
X minus 170 over 30. Yeah. Okay. And then 0.675 equals X minus 170 over 30.
So what do I get?
Hell if I know.
Just do the math. I got 149.75. And if I do the same thing for the other one, what do I get for the other one?
I got 190.25.
190.25. So therefore, what is the IQR?
$40.5.
40.5. So that's option one. You want to see option two?
Is it here?
Huh?
Calculator.
Data.
Calculator.
Or calculator. So go to seconds, vars. Now, if I have my z-scores and I want to calculate my proportion, I use the normal CDF. What if I have my proportion and I want to calculate my z-score? Which button on there do you think is the appropriate one?
D?
Which of those, if you look at the list, second vars, which list, which thing here do you think is the appropriate for going in the opposite direction for the normal?
In norm.
Inverse normal or inverse norm. And when you click on the inverse norm, this is what I get. I tell it, give me a 50% in the center when the mean is 170 and sigma is 30.
Wait,
And
area is 50%.
Yeah, we want the middle 50%, right? And it gives me the cutoffs to be 149.7 and 190.5, which are very, 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 very close to what we got from the table.
When I do inverse norm, it just gives me the options of area, mean, standard deviation, and paste.
Oh, yeah, it's a shame. What your calculator does, unlike my super amazing calculator, is what your calculator does is it only gives you the option of area to the left. So if I want the middle 50%, if I want the middle 50%, but I can only get area to the left, and I'm interested in this number here, what do I got to put in for the area?
Wouldn't that be 75, right?
75% or 0.75. And if I want this, the other edge, what do I got to put in for the area?
25.
25%.
How
So-
do we know that?
Huh?
How do we? Is it just it's supposed to equal 100%?
Well, that's one of the two conditions for a density curve. It's got to be non-negative. It's got to add to 100%.
But didn't we say that like it's 99.7, so it's not exactly 100?
No, I said 3 deviations takes us to 99.7, but you can go past 3 deviations. One
Oh.
68, another 195, 399.7. You can go on forever.
Those are the deviations, but everything under the curve is going to equal 100% no matter what.
Everything under the curve has to equal 1. It's a basic calculus technique in multivariable calculus, calculus 3, to prove that the area under a normal curve is 1. You can't do it before you hit multivariable calculus, but with it, it's pretty straightforward. But 3 deviations is about 99.7.
So I would put for the area 75, put the mean, standard deviation, and just paste.
And that would give you this number right there.
Oh.
And if you do 25%, it'll give you that number right there. That's Q1 and Q3. And then you just subtract them manually, and that gives you the IQR.
How come?
Yeah.
How come my calculator does it? Because I have a TI-84 plus.
I think there was more than one version of the TI-84 plus. Mine is a TI-84 plus CE. It's very fancy, this plus CE. But anyway, some do, some don't. This one does. What can I say? So that's it for,
I was gonna say, if you do like 1,000 standard deviations, it would be like 99.99999%.
Yeah,
Okay.
that's exactly it. It'll never reach 100, but yeah. So I put up the quiz just now. I opened it up. You have till 8:15 to do it. It closes at 8:15. That gives you 18 minutes for 3 what I hope are relatively basic questions. And you can do it and you can, I mean, you can go when you're done. We're done teaching for today. I did finish chapter 3. So, the whole, yeah, question?
Where's the quiz on Canvas or?
Oh, let me link it on, hold on, let me link it on Canvas before I forget. Sorry, I always just instinctively forget to do that, so hold on. It is on Launchpad if you want to go there immediately, but if you give me just a second, I will link it on Canvas.
Where is it?
I'm sorry?
Where's it on Launchpad?
Yeah, where is it?
Hold
chapter
on,
1 quiz, right?
hold
Yeah,
on.
yeah,
hold on.
I see
Chapter
it.
1 quiz. I just linked it, so you should be able to find it now on Canvas as well, but it is called the chapter 1 quiz. And on Canvas, I think I have to assign it. Yeah, okay, chapter 1 quiz. Due February 8th at 8:15 p.m. That's 17 minutes from now. You should be able to access it on either Canvas or Launchpad. Are people on there yet? Do people find it? Did it work?
Yes, it's there.
Okay, 3 questions, multiple choice questions, should be very straightforward. Philip, do you still have a question or did I answer it?
I still have it, but I'll ask after the quiz.
Well, I don't want to stick around, so go ahead and ask it now.
It was about the thing you just had up, the question we just did.
Oh, okay, go ahead. What's your, I'll put it back up.
So I was with you until you got, I think it was 149.75.
Yeah,
I think that was the 25%. And so so you subtracted that from 170, and that's how you got, I believe it was 20 and a half.
well, 149.75 is the X value for the 25% cutoff, right? For 25%, right?
Yes.
And 190.25 is the X value for Q3, right? Because we did both of them.
Yes.
And then just subtract
Yeah.
those two numbers and that gives you the IQR,
Oh,
right? Q3 minus Q1, that's the IQR.
yeah, because I said, I don't know why, but I did 170 minus the 149.75.
That
And
gives
I
you,
just doubled that number because that gives you one side, right? That gives you the 25%, and then you double it to get to 50.
that will work for a normal curve because it's symmetric, but it won't work in general. But
Okay,
it
so it's
will-
best to do the other way.
Well, I mean, listen, I mean, when you're learning something and you have a shortcut for a specific problem, because your understanding is deep enough to recognize that the shortcut exists, you certainly want to use that shortcut. But you want to be aware that it is a shortcut and it's not a universal approach.
Thank you.
But here you can certainly use it. Okay, any other questions?
Professor, really quickly, on this example, on the calculator, what did you enter on the under area?
Do you have the option of left, center, and right?
Yeah.
Then I did 50%, 0.5.
Oh, 0.5, and then it was just 170/30, and then I just left it under left.
I'm sorry, you
For
don't
the
need left. If you have center, you don't need left.
Oh, okay, so
It's 50% of the center. You wanna-
okay, I
you
see
wanna
what
click
you mean.
center.
Okay, cool. All right, perfect. All right, thanks, Professor.
No problem. All right, yeah, go ahead.
What was the first lecture, if I recall, the one with like it's the IQR times the 1.5?
That was determining whether or not something is an outlier.
Okay.
And I actually looked up today because I was curious about the whole why 1.5 was chosen. And it actually connects to today's lecture, because if you do 1.5 times the IQR, it should actually take you to roughly 2 and -2, which is our standard. These are outlier region. So the reason why
see.
1.5 was chosen because it works with a normal curve that way.
I see.
So I actually found that out today. I never knew that. And I was tutoring someone and I'm like, hey, why is it this way? And I went online and hey, the answer was there. Anyways, I don't want to talk too much because you're taking the quiz. Any last questions before I stop recording? Again, chapter 3 is complete, which means the homework will be due on next Thursday, which is actually after we're back in session. So yay, and we'll start chapter.
Wait, where's the quiz exactly right now?
It's on Canvas and it's on Launchpad. You can access it either place. It's called chapter 1 quiz. You should find it with all the assignments on Canvas, and you should find it on Launchpad. Anyone still having difficulty finding it? Yes, no? Everyone okay?
Yeah, I see it now. Okay, thanks.
Professor, in chapter 2, homework's due tomorrow, correct? Or in 2 days on Thursday?
Yeah, do Thursday.
Okay, thank you.
Sure.
And one more thing, you said you mentioned about confidence interval percentage. Should we worry about that now? Like pre-learn that, or
Don't worry about that. Confidence intervals.
got me scared because you're like, that outside that percentage, eventually we're gonna be tackling
Yeah, so don't
based
worry
on
about it.
like its confidence. Or
We'll tackle it later.
just worry about empirical.
Yeah, don't worry about it. I find that if you have motivation for learning something, like why it's useful, you're more likely to focus on it as opposed to an abstract. Oh yeah, one day you might need this. But that's just me. Okay,
When you finish, can you, sorry.
yeah, when you're finished, you can go. I'm actually gonna close the canvas down, so I can start recording, not canvas, the Zoom. So I can transfer the recording and have it saved, because I gotta leave and I can't do it till, yeah, whatever. So you guys have 10 more minutes. Once you're done, I'll see you guys on Thursday. Enjoy the whole new homework. Details, I don't even know what to call it. And I will see you guys on Thursday, okay?
Bye, Professor. Thank you.
All right, guys, have a good night. I'm gonna shut it down right now. It's gonna close for everyone. So I will see you guys.
Professor.
All
See
right,
you. Take care.
bye, guys.
Sounds good.